If you look up the Nernst equation in different places, you'll find it sometimes written the way that you see on this page, and other times you'll see things all packed together to give the Nernst equation for an entire cell. I'm going to entreat you to just do the Nernst equation for each of the two half cells separately, and then decide what the voltage will be for the entire cell after doing it piecemeal. It'll keep the equations a lot easier to handle, and it'll also keep it a lot more clear what's happening with each of your two half cells. And clarity is a major issue when it comes to electrochemistry. You want to stay as organized as possible. Now, let's take a look at this equation and the pieces and variables that are inside of it. So this is going to be our Nernst equation. I know I'm going to come back to that block of text at the top of the screen in a second. This is our Nernst equation for the half reaction. Now, we just saw something about this E naught. E naught is going to be the potential, or reduction potential for standard conditions, and this is going to be a reaction property. It's not going to depend on concentration or stoichiometry or anything. If I decide to write the exact same reaction, but I'm going to have 3 moles of reactant making 3 moles of product, it doesn't matter. We're still saying that the Nernst equation says that the potential is going to be the same between them. Now, think through that as being kind of like in thermochemistry when we say delta H of reaction is a certain amount. We don't care about the number of moles of that object that we have there yet. We're just calculating the potential difference when we do that. Well, that's the exact same idea that you want to be thinking of for these Nernst equations and these E naught values. Now, E naught is great because it's a table value. But what are we typically going to be using? We're typically not going to be at the same conditions you need to get A naught. E naught. To get E naught, you need to do that at activity equals 1 molar. Well, activity equals 1. We don't really say a molar for activity. But since we're saying that activity should equal concentration pretty close, in other words, our activity coefficient equals 1, then this is all going to be true. So you can think of it as concentration equals 1 molar, activity equals 1. We're going to be at 1 bar, which is going to be roughly 1 atmosphere, but we actually use the bar as our proper SI unit when it comes to this. And we're going to be at 25 degrees Celsius. So we're going to be in a fairly warm room temperature laboratory. We won't be at 20 C, we'll be at 25. Those are the reaction conditions that are standard. And when we do a cell, when we make a half cell and we connect it to the standard hydrogen electrode under these conditions, we will measure that voltage to be E naught. But usually we won't be under that very specific set of conditions. In fact, we really do want to be able to change our concentrations. So instead what we're going to do, we're going to plug in our starting value, E naught, and then this whole piece is going to correct for all the other things that we're having. We're going to have the ideal gas constant, R, in there. We're going to have our temperature present in that as well. We're going to have the number of moles of electrons. Let me emphasize that. Number moles electrons. And we're going to have the Faraday constant, because we need to do something to convert from moles into voltage. And that's what the Faraday constant is going to do. Then we're going to take the natural log of Q. And remember, Q is our equilibrium quotient. So just like we did back in all of our equilibrium problems, if we have A yields B plus 3C, if we were to write that as Q, then we'd say Q equals, and then we have our reactants on the bottom with their stoichiometric coefficient as the exponent. We usually don't write the 1, obviously, but I want to emphasize it for a moment. I'll do B up here, and then we'll do C to the 3rd power. We've already done that back when we were handling equilibrium problems. We're doing the exact same thing here when we go into Q. Now, for standard conditions, if we had all of these conditions true, and we plug that into Q, notice that Q is going to end up being the value 1, which means ln Q is going to be 0, And so if you are completely at your standard conditions, including your concentrations, then unsurprisingly, if you're at standard conditions, you get the exact same value for your E naught. So you can kind of think of this as being a little bit like an equilibrium coefficient in some ways. With an equilibrium coefficient, you had some idea of what you had for your starting range, but then you also knew that you needed to figure out your experimental conditions and how far you were from that central point. Same idea here. Now, we also like to have a simplified form to go a lot faster in our calculations, because notice, let's see here, this is a constant. If we're under standard conditions, that's a constant, and Faraday's constant is, well, a constant. And the conversion from ln to log is also a constant. So what they did is they rolled all three of those numbers and the conversion factor here into this value. So as long as you're at 25 degrees Celsius, or you're pretending that you are, you can use this equation. So E equals E naught minus this value, V is just my unit voltage, it's not a variable, divided by the number of moles of electrons, times log of my reaction quotient. Now, make sure that you use log here and not ln. We use ln for the complete version. We use log for this version. Why? Notice that log of Q is going to be basically a P whatever unit. So like pH or pKa or something like that. It keeps things a little bit more comparable in some of the chemistry calculations we do later on. Now that's the Nernst equation for a half reaction. I'm going to combine this video to include the Nernst equation for the whole cell. What we're going to do, we're going to solve the Nernst equation for one electrode, and then we're going to do it separately for the other electrode. And we're going to plug the answers in right here. Now, our positive electrode or our negative electrode, remember under our convention, that's going to be the right electrode minus the left electrode. This will tell us the voltage spontaneously occurring as we have it set up. And remember that whatever sign we get tells us the spontaneous direction as well. So if we end up having a positive value like we expect, then we have value, and we have our current flowing from our left side over to our right side. So negative voltage means we're going from right to left. Positive voltage means we're going left to right. Now, here's something else I want to point out, and I'm doing so a little bit early. In chapter 15, which I know is not where we're at right now, but very soon what we're going to see is that can't we force this reaction to go the other direction by applying some sort of an electrical current? And we know darn well we can. We unplug our laptop and walk around with it using the power from our battery. And that battery is discharging spontaneously and giving us a certain voltage. Until finally it drops to a certain point where we have to plug it back in to charge it. We're putting electrons back into one side. We're taking them out of another side because we're using an external power source. Okay, in other words, we can force those reactions to go backwards. The thing we're going to find out soon, we have to apply more than that reverse voltage just because we actually have to go over, and for this I have to remind you of something you probably remember from organic chemistry. When you have a reaction, you're going from your starting to your ending point. There's usually also an activation energy, and you have to get over that activation energy to actually get from one place to another. That's what's going to happen. When you apply your electric potential, and when you connect things and you're getting your voltage out, this would be your voltaic potential. This is what you're seeing come out of your battery. If you want to force reactions backwards, you have to exceed the activation energy, which means you're going to have to put in a higher voltage in order to charge it. So if I have a 15-volt battery that discharges, maybe I have to go up to 16 volts or something. Now, that's going to be important, and we're going to talk about it more in Chapter 15. For the time being, I just wanted to point out that if we have it written backward from our normal way of writing it, such that we have the negative voltage, That tells us that that's kind of the minimum idea of how much power it would take to recharge that battery and force the reaction to go as we have it written. In other words, have the reactions go the wrong way for the spontaneous way we're expecting. It's going to take more. That's about all I want to say about the Nernst equation for a whole cell, and about all I want to say for electrolytic cells for the time being.